Again, welcome to College Algebra. In these lectures, we're going to discuss about operations on functions. So we're going to focus on how to evaluate composite functions. A composite function is a function that is inside another function, or a function that depends on other function. And also, we're going to determine the domains for the composite functions and how to write functions as compositions. Then we are going to use the skill on operations of a function to solve application problems. So first, we start with evaluate composite function. As we said earlier, again, composite function is a function that depends on other function or is inside other function. So here we say often one quantity is a function of a second quantity that depends in turn on a third quantity. So for example, if we have a cost of a car trip is a function of the gasoline consumed. Why? Because again, the car depends on gasoline in order to move. So a cost of a car trip, it will be the function of the amount of gasoline that was consumed. So the amount of gasoline consumed in turn is the function of the number of miles driven. So the more miles we drive or the less miles we drive, the gasoline consumption either will go more or less consumption. So such chains of dependence are analyzed mathematically as a composition of functions. So again, a composition of a function is one function depending on another function. So for example, we have a composite function f and g. Again, composite symbol is the circle or a dot with a hole, either small circle or a dot with O. The symbol here means composite, F composite G. Now, since F comes first, G will be inside of F. So we can write F composite G at X, which means G at X is inside F at X. Now, if we have G composite F, then we're going to have G at F at X, which means F will be inside G. So the domain of F composite G normally consists of all those numbers in the domain of G, for which G at S is in the domain of F also. So we can see the diagram here. Again, we have X, then we have G at X, then we have F at X. Now the composite, which will be F composite G, will move on the red circle. So in this case, G at S is inside F at S, or depends on F at X. So let's try an example here. So we have a function F at X equal to 2x plus 7, and also G at X equal to x squared minus 1. And they say we should find F composite G at X. This means anywhere we see, first of all, we write F at X down, and anywhere we see X, we replace it with G at X function. Then we solve it. The other way, G composite F means we write G at X down. Then anywhere we see F at S, we substitute with the X. So for example, in the first part A, because F composite G at S means F at G at S, we will replace the X of the F at S with G at X. So F at S is 2x plus 7. Anywhere I see X, I'm going to replace it with a function of G at X, which in this case it will be x squared minus 1. So at the end, we are going to get 2 times x squared minus 1 in a parenthesis plus 7. Then in part B, we have G composite F at X. So it will be G F at X. So we are going to write the g at s first, which is s squared minus 1. Now, anywhere I see x, I'm going to substitute with f at s, which is 2s plus 7. So I'll get 2s plus 7 all squared minus 1. So let's solve the problem in the next slide. So we have f composite g at x. Since f comes first, is the same as writing f g at x. So I'm going to write f at x down. Now, anywhere I see x, I'm going to replace with g at x. So the g at x here is s squared minus 1. And we know the f is 2s plus 7. So it will be 2s squared minus 1 plus 7. Then we solve for it. So this will give us 2x squared minus 2 plus 7. We combine minus 2 and positive 7. We get 2s squared plus 5. Now, the same thing applies to g composite f at x. Since g comes first, it means it will be g at f at x. So replace f at s with its function. F at s is 2s plus 7. We know g is s squared minus 1. So anywhere I see s, I'm going to substitute with 2s plus 7. So that will give me 2s. Since it's s squared, it will give me 2s plus 7 squared minus 1. Then we can open the parentheses here, and we get 4s squared plus 28x plus 49 minus 1. We combine the constant values, so our final answer will be 4s squared plus 28x plus 48. Again, we should be careful with the a and b. So when we have f composite g at x, it means we have f at g at x. So we substitute g at x in the parentheses, so we get f s squared minus 1. This tells us that when we write the function for f, anywhere we see x, we are going to replace it with s squared minus 1. Now, since the function f is only 2x plus 1, it will be 2s squared minus 1 plus 7. I mean, g at s is s squared minus 1, and the function f is 2x plus 7. So we substitute s squared minus 1 with x, and we get 2 multiplied by s squared minus 1 plus 7. Then we solve it. Now, g composite f at s means g at f at x. F at s is 2s plus 7. So now anywhere I see the function of g at x, anywhere I see the x, I'm going to replace it with 2s plus 7. And the function g at x is s squared minus 1. So I'll replace s with 2s plus 7 and it's squared minus 1. Then we solve it, and this will be our final answer. Now let's go to the next section, which is determine the domains of a composite function. Now, the strategy to determine the domains of f composite g is to determine the domain of f composite g at s equals f g at x. Now we need f at g at x. We need to apply the following restriction to the composition. Now we say that if s is not in the domain of g, then it will not be in the domain of f composite g also. And also any x that has an output g at x that is not in the domain of f also will not be in the domain of f composite g. So we have the domain have to be common among f at s and g at x, since the two functions composite. So let's see an example here. We have f at s equal to square root of x, g at s is x minus 3. And the question here says we should find the domain of f composite g and g composite f. So here we will first find the domain of f at x and g at x separately. Then we will find the domain of f composite g and g composite f by applying the restriction that we stated. The restriction said again, if the domain is not at f at x and g at x, then we cannot have it for f composite x. So you have to be common for both f and g. So now, first one, we know square root of x. Square root of x have to be a real number, which means s cannot be a negative value. So the domain of square root of x, which is f at x, will be s should be equal to 0 or greater than 0. So it will be from 0 to positive infinity. So that's non-negative real numbers. So from 0 to positive infinity. Now the second is x minus 3. X minus 3 can be any value. So from negative infinity to positive infinity. Anytime we are looking for a domain of a function, we need to consider two things. If we have a square root, the square root cannot be a negative value. If we have a rational denominator, the denominator cannot be 0. So those are the two main rules that can help us to find the domain of a function. So here we have only s minus 3. So the domain will be any value from negative infinity to positive infinity. The square root of x, it have to be only positive value. So it will be 0 to positive infinity. So now we know the common of the two. The negative part is not in square root of x, but all the positive part is in square root of x, and also is in s minus 3. So which means A, we will say that the domain of f composite G is the set of a real number x such that x is in the domain of G and G at x is in the domain of f. Since we have seen that all values of x are in the domain of G, however, G at x must be non-negative because G at x must be in the domain of f. So here we must find the values of x such that G at s is greater than or equal to 0. So G at s is greater than or equal to 0, s minus 3 greater than or equal to 0. So s will be greater than or 3, equal to 3. So since s should be greater than or equal to 3, the domain of, again, f composite G will be the interval from 3 to positive infinity. Again, the reason why is this because G at s is square root of x. The domain will be 0 or higher, so from 0 to positive infinity. F at s is s minus 3. The domain will be any negative infinity to positive infinity. But we can't use the negative part because G at s is a square root. It should be greater or equal to 0. So if that is the case, s minus 3 also should be greater than or equal to 0. Then we solve for x. So s will be greater than or equal to 3 means from 3 to the positive infinity. The same thing we are going to apply the rule for G composite F. Our first answer was F composite G. So G composite F will be the set of real numbers x such that x also is in the domain of F and F at s also is in the domain of G. So we have seen that only non-negative values of x are in the domain of F. Because all values of F at s in the domain of G, the domain of G composite F is the domain of F, which is the interval from 0 to, again, positive infinity. Because G composite F means F at s will be inside G. And we know that from the function, G is x minus 3. So if I'm looking for F composite G, then it will be F. G at s will be s minus 3. And also the other way, G composite F means we have G at square root of x. F will be inside G. So let's move on to the next section, how to write functions as compositions. So when we have formed a composite function, example f composite G, we obtain a function h. So it is possible to reverse this composition process. and begin with a function h and express it as a composition of two functions. This process means we are trying to break the function into two. So decomposition. Composition means we have something inside something more than, we can break it down more than once. Decomposition means we are reducing it. So now let's see an example. If we have h at x equal to square root of x plus 1, and the question said we should find two functions f and g such that f composite g equal to h. And this means f composite g is square root of s plus 1. Now we want to find f separate and g separate. Now because h again takes the square root of the algebraic function s plus 1, we let f at x equal to square root of x and g at x equal to s plus 1. Then we can check the composition to see that it will give us the original function. So in this case, I'm looking for f composite g. So what we're going to do is, anywhere I see square root x, I'm going to substitute with s plus 1. So here we can see that it works because I have only square root of x, and f composite g means anywhere I see x, I'm going to substitute with g at x. So I'll get square root of s plus 1. So that works. So that's what we are. F composite g at x will be f at g at x. So it will be fx plus. Now, since f at x is square root of x, we substitute s with s plus 1. So we get square root of s plus 1, which is the same as h at x. Now, we're going to use the operations on functions to solve one problem. This is application problem. So here we have a laboratory sample is removed from a cooler at a temperature of 15 degree F. Now, technicians then warm the sample at a rate of 3 degree F per hour. Express the sample's temperature in degrees Celsius as a function of the time t in hours since it was removed from the cooler. So to solve this problem, first we write the Fahrenheit temperature function that represents the warming of the sample. We write it down. Then we use the composition function to write the degrees Celsius as a function of degree of a Fahrenheit. So here we're going to have the temperature of the sample is 15 degrees Fahrenheit when t equal to 0. Now, because the sample warms at 3 degree F per hour, it will warm 3t degrees because t represents the time after t hours. Thus, the Fahrenheit temperature after t hours is given by the function f at t will be 3t plus 15, because the plus 15 is because the temperature of the sample is 15 degree F when we started, t equal to 0. Then it warm up 3 degree F per hour. T is our hours, so it will be, depends on how many hours, it will be 3t. So f at t will give me 3t plus 15. Now, the Celsius temperature is a function of the Fahrenheit temperature f at t given by the following formula. It will be 5. If I want to convert a Fahrenheit to Celsius, the formula is 5 by 9 f degree minus 32. So we substitute f at t in, and we solve the problem. So C composite f at t will give me C f at t, and f at t is 3t plus 15. The formula for C is 5 by 9, 3t plus 15 minus 32. Then we solve for the equation. So this is a concept of using a composite function. We are changing the degree from Fahrenheit to Celsius, and we have the formula 5/9 and T temperature in Fahrenheit minus 32. And since the Fahrenheit is 3T plus 15, we substitute it and we find the solution. So that will be the conclusion for these lectures. And again, wish everybody the best. Thank you.